Let's first start off, make sure we're in the right place. This is Lagoon GHI for ARM, IDA, and Crosscheck, reversing the Boeing 787's core network by Ruben Santamarta. Before we begin, though, we have a few brief notes to cover. Please stop by the business hall located in Mandalay Bay, Oceanside, and Shoreline Ballrooms on level 2 during the day and for the welcome reception at 5:30 this evening. The Black Hat Arsenal is in the business hall on level 2. And join us for the Pony Awards in Lagoon JKL at 6:30. Please put your phones on silent, and depending on the time of the talk, questions will either be at the microphones, or if not, we'll go to the wrap room at Reef A down the hall. So without further ado, Ruben.
Well, thank you very much, everyone, for attending today. It's also my third time in a row here, so thank you for Black Hat for having me here. I would like to introduce a little bit the context of this research. I've been afraid of flying for many years, so there are different ways to deal with this. I decided that my way would be to learn as much as possible about aircraft, and that led to this kind of research that I've been presenting for a couple of years or 3. Let's back to the future, because I think it's going to be interesting. 10 years ago, Wired published an article, a story on the 787. Basically, this was one of the most advanced aircraft ever presented, and it contained a lot of new functionalities, and all those functionalities came at a cost that basically they were mixing, or they were sharing a common network that in other aircraft or other designs they were physically isolated. It's interesting to read this article because, for example, the spokesperson from Boeing in that article says that the network is physically isolated. The different networks are physically isolated. So we'll see some things today that maybe that's not the right thing to describe how it's designed. Then we can move to, or we can jump to 2015. All this mess with Chris Roberts happened, and there was an article also on Wired that was discussing what's the reality, or what's the truth behind hacking an airplane. Peter Lemme, which is a former Boeing engineer, I highly recommend his blog. It's satcom.guru. Explained this, which is common sense. If you have a network-centric aircraft design, there should be something between the avionics and the in-flight entertainment system or other devices located in the non-critical domain that should segregate or prevent that all the traffic can end up in the avionics network. So today's talk is about that box. And that box in the 787 has a name. It's the Core Network Cabinet. But let's move to the beginning, how everything started. So in September 2018, just a month after giving a talk here about SATCOM vulnerabilities, I was trying my luck with some well-known Google queries. And it turns out that I discovered a publicly exposed Boeing server that contained quite a few files, and well, they looked interesting, definitely. So I downloaded everything, and later on I analyzed the files, and well, the result is that I had access to the 787 core network cabinet, also part of the 737 firmware, and also a virtual machine that Boeing engineers use to VPN in that specific Boeing network. I would like to clarify that the firmware that I had access is black label. It's production. It's not any kind of testing. It's black label, which is the terminology for production in avionics, and also it included the the documents and everything, and you can see that those details in the white paper that will be published right after the talk. So the methodology is like in the previous research. Basically, we are very limited. We don't have access to 787, unfortunately. If someone wants to offer, I'm okay. But, well, we have quite a few sources. We have documents, multimedia material, patents, which in this case was very, very important. And then we have reverse engineering, because we have the binaries, we have the firmware, so there is no option other than reversing the binaries. So, well, obviously the 787, as any other aircraft, is a very complex system, but just to put things into context, let's try to briefly explain at least a couple of questions or concepts about this aircraft or many others. So basically, we can say that in the 787 we have a component or a system that is the avionics, that it's the core of the aircraft, that is certified. It supports the common standards for avionics, and then we have the core network cabinet that is not. It's not certified, as we will see later on. So basically, in the common core system, which is the approach Boeing used for the integrated modular architecture, we have the general processing modules, which are basically all these modules have the same operating system, but they are running different applications. We have remote data concentrators, and we have the avionics network we were talking about, which is based on Ethernet, but it's adequated, it has been modified to support avionics operations. So it's quite complex. It contains different functionalities that obviously the regular Ethernet networks we are used to don't contain. It's important to say that it's a virtual system. Basically, they are using VxWorks CS53, which is a type 1 hypervisor. It's a bare metal hypervisor. And on top of that, they are running different partitions which contain different applications with different criticalities. So that's the platform. And if we take all those elements and we put all together in a cabinet, we have the common computing resource cabinet, which contains these modules we'll see later on. But it's important to note that these are the cabinets that are running the core functionality of the aircraft, the avionics part, basically the functionality or the functions that keep the aircraft flying. This is some of the hosted functions. We also have remote data concentrators, because on board the aircraft they have still some sensors, some actuators that are not enabled to speak RN664, so they use all buses or they use CAN bus, so they have to, the hosted functions can talk to those devices, to those sensors. So we need a way to talk to those sensors, and this is the way, the remote data concentrator. Here you can see an overview of the Boeing 787 and the different network from a high-level perspective. So we have the common data network, which is the avionics network, where everything important is connected to. It's a high-integrity network. The airplane systems are connected to this network. Then we have some remote network switches, the remote data concentrators, as I mentioned. Then we have a whole set of sensors, actuators, effectors. And then we have the core network cabinet, which is basically a window to the internal core system of the Boeing 787. If we oversimplify, it's like a way to interface with the outside world for the 787. This is a picture of the actual core network cabinet, and it's, as I mentioned, it's the interface between the outside world and the non-critical domains, and the common core system. So there are different modules. Not all of them are in the scope of this research, because basically we don't need all of them to compromise this device and bypass the security boundaries we need to bypass in order to reach the common data network, which is our goal. So the crew information service, the crew information system, which is the system that is implemented in the core network cabinet, is comprised of 3 networks, or it's handling data from 3 different networks. We have the open data network, where all non-critical aircraft domains, devices are connected. For example, the in-flight entertainment system, everything that is not secure or that is potentially hostile is going to be connected to the ODN. And then we have the IDN, which is the isolated data network, which is where some devices that are considered secure are connected, but they are not strictly related to the safety of the aircraft. For example, the black box of the aircraft, the voice and data recorder, or the electronic flyback. And then we have the common data network, which is the high integrity network, and the airplanes, sorry. And the airplane systems are connected to. And then the modules that comprise the crew information system are the following. We have the crew information system and maintenance system file server module, which is running a VxWorks 6.2, and it's not a certified VxWorks, it's a regular VxWorks, so it's not intended to be running on a certified avionics system. It's a commercial of the self board based on a Pentium M CPU. The VxWorks supports real-time processes. So basically, we have a user mode and kernel mode, and on the user mode side, we have these real-time processes, which are the functionalities that are implemented in the crew information system. Then we have the Ethernet gateway module, which is a Linux embedded device. Basically, it doesn't have any other particular characteristic. And then we have the network interface module, which is the end system for the RN664. So what's the attack surface of the core network cabinet? Okay, so basically, if we go to the US patent on that one, that patent basically covers the entire system we are talking about, and it was really helpful to try to understand the whole picture of the system. And as you can see here, these modules are providing the segregation between the network devices in the IDN, the isolated data network, and the CDN. So obviously, if we can bypass the security boundaries of those devices, of those modules, we can reach the CDN. So this is basically the security boundaries we're talking about. We start on the ODN, where, for example, the in-flight entertainment system is located. So what are the security boundaries starting at that point? We have the EGM, the Ethernet Gateway Module, which is implemented a firewall with basically IP tables and a set of rules. And then we have the crew information system maintenance system module, which is running VxWorks, and it's implementing also a packet filter functionality with the firmware FWlib, which is custom for VxWorks. And then finally, we have the network interface module, which is the end system for the ARINC64. And this is the last security boundary. So this is basically configured through this proprietary binary file, which is generated with a tool that is certified as level A, which is the highest certification for the software assurance in avionics. So the base or the common attack scenario for this architecture would be as follows. We start on the ODM, we potentially find a rule that is allowing us into the crew information system. Then we have to exploit the crew information system to gain remote code execution. And from there, you can see, we can jump to the network interface module. And from there, we are just one step from the CDN, and that's transparent for the attacker. So once we are going to talk about that later on, but once we reach the network interface module, which is the last device before the avionics network, we have to find the rules that allow us into the CDN, because it's not possible to reach all the avionics nodes that are connected. So this is the attack scenario. We have the regular flow. Basically, this is the way the system has been designed. Some operations, some devices require access to certain functionality in the common core system, and they go through the regular flow, through the EGM, going through the boundary router or the crew information system, and they end up in the CDN and the common core system. Okay, so what are we doing? We are taking an alternative approach. We start on the ODM. We go through the EGM by abusing a firewall rule, if we can find any, and then we exploit any network service that is running on the crew information system, and then we take control of the crew information system. From there, we can go to the IDN switch, and from there, we can, according to the rules that are being implemented in the NIM end system, we can move to the CDN switch, from there to the common core system or other views. So our task here is to find a way to exploit something in the crew information system, and this is how the firmware is organized. So we have the VxWorks kernel, then we have the user mode where we have up to 14 real-time processes, and those real-time processes are sharing up to 15 cert libraries, including libc, which I think it's not there, but yeah, they compiled a specific libc version for VxWorks. This is important for a question we are going to talk about later on. So, some vulnerabilities that I could find here, hundreds of references to insecure functions in 2019. A sprint, a string copy, string cat, all in the set. Integer overflows, buffer overflows, denial of service, memory corruption, out of bound read and write, everything, it's there, basically. So I'm not talking about all the vulnerabilities. Here, we are just going to document a minimum set of vulnerabilities that allow the SIS to be compromised. So in that way, we know that if we use those vulnerabilities, we can compromise the SIS and reach the part of the network we want. Basically, we are going to explain remote code execution and privilege escalation to kernel. So the first one, remember that we had to find a rule in the EGM that allowed us access to a network server or network service exposed by the seas. So there is one, the FTS manager, which is implementing some file transfer services, and TFTP server basically performs the following operation. It's listening for TFTP connections on different ports. One of them it's allowed from the EGM. The port is the 16005. Basically, they are receiving the request of 200 bytes, and they are taking the first bytes, which is the TFTP opcode operation, and they are using that index into an array of operations just to, you can see, to generate a log. So how we can exploit this? There is a problem here because the server is only receiving 200 bytes, but on the other hand, and the log buffer is 400 bytes. So we don't have enough content to overflow the buffer. So we have to wait. We have to find a way to find a string that is long enough, and we can use the opcode index to find that string. Basically, as you can see here, in this operation, we can reference any string in this range, which covers part of the data section and part of the BSS. And the analysis of those sections gives several targets that can be used to obtain a large enough string that can be used to overflow the buffer and gain remote code execution. So you can see here part of the rule that allows this kind of traffic. This comes from the file S24 EGM config, which is the official file. And you can see how this traffic is allowed. We have the in-flight entertainment system router, which is at the ODN, the 40.2, and then we have the crew information system, which is the system that we are exploiting in the IDN. And you can see how it's allowed. So also in the network interface module boundary router, we find the same rule. So basically, in the boundary router of in the file AIM config.xml, Boeing or Honeywell or the manufacturers of this system are setting or are configuring the rules that allow two things: the communication between the EGM and the boundary router, and the communication between the NIM and the CDN. So this is the attack scenario for this exploit. Basically, so far, we have, for example, the in-flight entertainment system router, which has been compromised. In other talks, we have seen how to do that. In past year's talk, I presented how to access the in-flight entertainment network from the ground through a satellite communication device. So it's something that can be done, obviously. And we go through the EGM using the rule that we have seen, and we exploit the network service that is running and it's vulnerable. Then we compromise the crew information system and reach the network interface module. Let's move to another vulnerability. In this case, it's not an insecure function, it's just another vulnerability pattern. So this is located in disk utils. but we can exercise the vulnerable function path from the ODLF, which is the onboard data loading function, which is one of the functionalities the core network cabinet is supporting, which is allowing the technicians or allowing the airlines or Boeing to push firmware updates to the aircraft. So you can see that in this case, the loose file is part of the TFTP or part of the RN615 protocol, which is or standard, better said, which is based on TFTP, and it's used in avionics to upload a new firmware to line repressible units. So this, the attacker is controlling this file, and the library is trusting the contents of this file, so we can control the number of headers, and then there is a for loop where they are using the number of headers as an index into a fixed array of structures that is located in the stack. So again, we can overflow the stack and overwrite the memory in a controlled way. We can control the execution, and this can be exercised from remote. You don't need to be authenticated as well. Another vulnerability similar to the previous one in another file that is part also of the RN615. In this case is the FSM target loader, which is the functionality which is updating the firmware for the own file server module, for the own crew information system file server module. In this case, as you can see here, again, the attacker is controlling the load, the LUOH file. We can control the load part number length, and then there is a loop where we can overwrite the stack with controlled values, and again we can control the execution of the code. Again, it can be exploited remotely without being authenticated. Okay, so we have 3 different vulnerabilities to gain remote code execution, and then we have to find a way to escalate privilege to kernel without needing to reboot the device, which is obviously the most interesting option is always to escalate privileges without rebooting the system. So I was analyzing the kernel, and the Honeywell, which is the company that develops this firmware, created a new group of system calls for the shared libraries. And you can reach those system calls using a call gate. So I was analyzing those syscalls, and basically they are not validating anything. So you can read or write arbitrary memory. They are also using insecure functions, pretty much the same than in the other binaries. There is an interesting syscall which is used by the real-time processes to add rules dynamically to the firewall that is implemented in the crew information system. And this is useful to unblock CDN access during the exploitation phase. So you can see the code here. The first function is the system call handler. Do you see any verification of the memory? No, there is no verification of the memory. So that's the thing. So the next one is the actual functionality, and you can see that, well, they are using also a sprint and everything. So obviously there are many ways to escalate privileges using these system calls. Basically, in any of the system calls, they are performing validation. So it's just you just need to choose the one you want. So again, back to the attack scenario. We are going to update a little bit from ODN to CDN. We have, again, our malicious flow. An attacker is starting from the in-flight entertainment system router, which has been compromised. Then we have exploited the crew information system, which has been compromised. And then we reach the network interface module. As I mentioned before, we have the end system that is controlling when, how, and who can send or receive information from the RN64 network. And the last part is to find a way to leverage our access to the avionics network, because at this point, even if we can access the avionics network, it doesn't mean we can reach or we can do anything. It depends on the end system in the network interface module. So this is a potential attack scenario for the in-flight entertainment system to the CDN. Basically, is what we have been describing. A second attack scenario is from an arbitrary line replaceable unit to CDN, and this is similar because we have to understand that the ODLF functionality that allows to update new firmware to these LRUs can be used to exploit the crew information system. So imagine that we have a compromised LRU that is going to receive new firmware. We can trigger the exploit against the updater, and in that way we can have access to the crew information system, the IDN, and eventually the CDN. There are other potential scenarios. For example, many of you probably know that there are emergency lighting systems in the aircraft, but maybe you don't know that these are running some wireless protocols. So that's also an option. In this case, this is this is an attack scenario. We didn't elaborate it. We don't know if that specific product contains vulnerabilities or not. We are just potentially illustrating an example. In this case, the onboard attacker that is able to compromise the wireless controller unit of that specific product can wait until, again, the ODLF functionality will push a firmware update to that LRU, and then again will trigger the exploit against the ODLF. You can see again the rule that is allowing this kind of connection, which is important to mention because of the claims I've been reading in the press lately. Another option is the scenario 3, which is an external network to CDN. This is probably another worst case scenario. The 787 supports different communication links, SATCOM or cellular, or what it's called the Gate Link 822, which basically it's a wireless infrastructure that is located on the airports, in every airport almost. So when the 787 lands and goes to the gate, it connects through the wireless, through a specific wireless, the Gatelink 822 wireless, to a specific server that is configured in the aircraft through a specific file, which is the LDI.bin. So the external server the aircraft connects to is what is called the airline LSAP proxy, which is basically a server where the airline, the manufacturers, or any other entity can push firmware updates or can push commands. And when the aircraft connects to this server, it will receive those commands, it will receive those firmware updates, or it can send it can send data to the remote server. There is a bidirectional communication between those servers. So we discovered at least 2 different internet-facing vulnerable LSAP servers belonging to 2 different airlines. We notified Boeing about this, and at this point, those servers are no longer available. Obviously, once you compromise those servers because they were running vulnerable services, you could find those servers using Sodan, so it was pretty easy. You have access to certain functionality, and you can use this functionality to potentially compromise certain functionalities within the crew information system. Also, it's important to know that the gate link may pose also an attack vector in the airport. For example, not all the airports implement the same way, but in the Madrid airport, you can, in the Terminal 4S, you can see the gate link 822 Wi-Fi broadcasting all the time. You can, obviously, still you need certificates to connect, but it was interesting. Another scenario is the TCU or any other communication link that the Boeing 787 supports. For example, if the SATCOM, like we saw past year, is exposed in the connection, you can potentially use the rules that are allowing certain connection from the TCU to leverage certain vulnerabilities, like we can see, but it was pretty much the same that the other scenarios. So once we have reached the CDN, the avionics network, what can we do after that? Okay, so in this case, the configuration files we have been analyzing, and basically how the system has been designed, because it's documented in the patents everywhere. You can write or you can read that in the white paper, and you can use this information to investigate further into these issues. So there are mainly 2 options once you are there. You can initiate a potentially malicious firmware update against safety critical units. This doesn't mean you can, but there is an option because it's supported by the system. And you also can abuse the maintenance functionality. Obviously, this can be used to deceive some maintenance engineers receiving malicious information or thinking everything is correct. Maybe it's not. There are different options. But it's important to say, we are not exploiting anything on the ARINC64 network. We are just using the system in the way it was designed for. This is important also because I'm reading some claims from Boeing in the network, in the press, that don't make sense to me. So what are those safety critical systems? Well, there are 21 remote data concentrators, and these are connecting to the following safety critical systems, which basically some of them, and most of them, obviously, that's the reason, because they are safety critical. If something fails, then the aircraft is in troubles. And this rule to demonstrate that it is possible to initiate, for example, in this case, against a potentially malicious firmware update against the electronic engine controller, it is bad if you can. You can see the rule that is allowing this kind of connection. The EC controller, which is an IP from the CDN, and then we have the IP from the IDM, which is the crew information system, which is the system we can compromise using our exploits. And obviously the TFTP board, where the firmware update is going to be initiated. What about maintenance operations? Where there are three different parts or three different modes for maintenance. The wired, basically, if the maintenance engineer goes to the cabin deck, to the flight deck, and connect the laptop to a wired connection, it has full access, or he or she has full access to the maintenance operations. But you can also use the crew wireless LAN unit or the terminal wireless LAN unit to connect to the maintenance network. And if you connect through the wireless, you don't have access to everything. You need an additional step. You have to enter a code that is generated in the crew information system, the system that we have compromised, in order to reach the CDN and to reach all the functionality of the maintenance operations. You can see how that code is generated, and the maintenance engineer has to enter this code through a cabin interphone, which has an important implication, which is also that the cabin interphone may pose as a threat or may pose an attack vector because of the vulnerabilities we have seen. Well, the maintenance operations, it's implemented in the common core resource cabinet. And I think I'm a little bit tight in time, so I really want to talk about this, about the responsible disclosure. Okay, so we obviously contacted Boeing about this, and we provided the information, all the detailed information about the vulnerabilities. Boeing and Honeywell confirmed these vulnerabilities, but they didn't confirm they are exploitable. So basically, they say these vulnerabilities are in the current code base of the 787 core network cabinet, but they have done their own testing and they couldn't reproduce the issues. So they say that this is not exploitable. They also mentioned that they have compiler level mitigations in place to prevent these vulnerabilities from being exploited, but they didn't provide any details. So what happened during the disclosure process? So they did insert versions. So we the firmware we had, they from 2016. We don't know the version of the system they have been testing. They did insert this information even after we requested it several times, because obviously it's an important thing to try to solve discrepancies. If they say this is not exploitable and we say yes, at least we should reach an agreement on the versions they are testing. We also didn't have any visibility over the testing plan. We don't know what kind of techniques, exploitation techniques they use, or what kind of test they use. We don't know anything about this. First of all, they asked us to sign an agreement in order to provide this information, and this agreement was signed, and they said no. So, well, fine. Mitigations. So basically, also, according to certain claims I'm reading on the press right now, Boeing claims that there are certain mitigations, compiler level mitigations or network mitigations that prevent these vulnerabilities from being exploited. Well, regarding the compiler level mitigations, we analyzed the binaries, obviously, to see if there is any compiler level mitigation, and there is no compiler level mitigation in the binaries. So we asked that maybe those mitigations were added later. Boeing declined to answer even this question, and Honeywell is checking this today. So it's fine as well. But there is an additional response from Boeing, which is basically they decided, okay, IOActive reviewed only one part of the 787 network using rudimentary tools. So this is IDA Pro, which all of you know it's pretty rudimentary. It's like hitting the laptop with a rock and the vulnerabilities jump off, and that's it. And they also decided that IOActive choose not to ignore our verified results. That's not true. What I didn't choose was what to believe in magic. So I'm reverse engineering the binaries that are running in a common commercial off-the-shelf CPU in a common device, embedded device that happens to be connected to the avionics network. I've been doing this for 20 years. I do this every day on my regular job. So I will accept any technical details. But well, some of the claims they mentioned is like, okay, IDA is a rudimentary tool, a sprint can't be exploited, or a rope chain can't be used in a real-time operating system because there is not enough functionality, which is something I can't even say, you know. And also, compiler level mitigations can work even if they are not added to the resulting binary, which is pretty, I mean, it's a new paradigm to the computer security, so that's it. But again, I really want to go further, investigate, and provide the details to Boeing and to everyone. So I decided to take a look at the mitigations. I don't know exactly what's the model of the CPU they are using in the board, in the commercial of the self board, because there are different revisions. But I can analyze the VX words and see if they are. What I know is that it's a 32-bit CPU. So if they are, for example, if they claim they have no execute, which is not something they claimed, but I was trying to investigate. Well, the only option is if they are using the PAE bit, which is not. You can see how those two bits, PAE and PSE, are cleared, and then the CR4 register is set, so no option for no execute. So even in this case, there is no need for a rope chain. You just need to use exploitation techniques from 20 years ago, 15 years ago. What about GCC stack mitigations? All right, okay, they mentioned that even insecure functions couldn't be exploited. Okay, let's see the implementation of a string copy, for example. Do you see any protection there? Because there is no protection there, obviously. They are just copying the string to the buffer, and that's it. So it's exploitable. Let's move to another function to see if the stack protector has been added. This vulnerable function, which is from the FTES manager, has a significant stack frame, which should be a trigger for the stack protector from the GCC. Again, no results. There is no stack protection. There is nothing. So, I mean, they say this is not exploitable. They say they have additional, I don't know, magic or something like that, that prevents these vulnerabilities from being exploited, but they are not going to share any information about this. And to be honest, it's hard to believe that they are having such a firmware running, but then they have a super secret system somewhere that is able to prevent this kind of exploitation on a commercial off-the-shelf board. So I'm sharing all these details because this is a talk, this is a research for the security community, for all potential companies affected, for everyone who really wants to investigate further into this matter and reach their own conclusions, because you don't have to believe me. You don't really need to believe me, but it's important to share the details because it can be used to motivate, and it can be used to let the people who really have the access to those kind of systems investigate further into this problem. That's all. Thank you very much. Thank you for having me.